into this same size capacity knapsack. So it would just be the row above, because this is for all the other items for the same capacity size. That's 12, so it's obviously better to put this item in and then use the value here of this sub-knapsack problem. And this is what dynamic programming is all about. We've already worked out some of the solutions. We've already worked out an answer to the capacity of 4 with one item, with the other items. So we just use that in our sub problem to work out the best solution to fill the space, basically. And we see that that's the best thing, so we stick it in there. Now for these other 11 to 18, it's just going to be the same, because each time it will make that same calculation and the same result will occur, basically. Except each time the space will be different. So for example, for 14, we look at the value of this item, we subtract 6 from 14, we're left with 12. So we look at we're left with 8, sorry. So we're left, so we look at this answer, the 8, for all the other items. And then that's what we do. Those are the 3 checks we do. Will the item fit in on its own? If it doesn't, then use the row above, because that's for the other items, right? The best solution using the other items. If it will fit in on its own, do we fit it in and then solve the space and add it together? Or do we not fit it in and just use the same solution for the other items of the same knapsack capacity size? Alright, so now we're going to take into account the first 3 items. Capacity of 0, well, we get 0. Capacity of 1, still 0, we can't fit anything in. And this first check is failing every time because we can't fit this item in on its own, so we're just taking the row above. Up to on 4, we still can't fit this guy in, so we're taking this row above. On 5, things are slightly different because the calculation that's occurring here is, well, we can fit this in, this weight of 5, into this knapsack of 5. So if we did, we'd have a value of 8 and we'd have a space of 0. So space of 0 for the other items has a value of 0. We look this up on the table here. And we add it to our value of 8. So we just have a value of 8 if we fit that in. Is that bigger than not taking the item and just taking into account the other 2 rows for the same knapsack size? So we look at this thing, because this is the capacity of 5 for the same knapsack rows, right? And it's bigger than 8. It's bigger than our other number, so we use 12. And that's basically all we do each time. We provide, oh, what have we got here? Let's just talk about this, and then I'm not going to go through any more. We have a capacity of 9, and we're saying, will this item fit in? Yes, it will. So which is better? We take the item and we pop it in the bag, and then we're left with a knapsack of size 4. So we look at the solution for knapsack of size 4. With the other items, it's 12. So 12 plus this current item, 8, is 20. So that's one value. That's if we take it. If we don't take it, we look at the same knapsack capacity size, 9, but for the remaining items, these guys. And we look at this cell here, because that is that knapsack problem. And it says 12. So, which is bigger, 12 or 20? 20. Okay, so we should take it. And we identify this in the keep matrix. So we do this all the way through, basically. It's the same checks that are going on every time. Will the current item fit in at all? If it will, then which is better? Do we take it or do we not? And the reason, and if we take it, the calculation that we need to make is I'm distracted by hitting the enter button. If we take it, the solution is the current value item plus the space that's left, the solution to the space that's left. If we don't take it, then it's just the solution to the problem for the other items, the row above, and ignoring this item. So we finished our table.